Hello students. So this question is asked from GATE 2024 ECE control system. Okay. Here they are asking that in the context of Bode magnitude plot, 40 dB per decade is the same as. I already told you that 1 dB per decade is equal to 0.301 dB per octave, if you remember. So I told you that 20 dB per decade will be same as 20 dB, 6 dB, 20 into 0.3 will be 6 dB per octave, and 40 dB per decade will be 12 dB per octave. We discussed so many times while discussing the Bode plot. Okay, so the slope will be given in terms of decibel per decade or decibel per octave, and you must know the conversion. So the right answer is 12 dB per octave for a 40 dB per decade. So this particular question was asked from the control system in GATE 2024 ECE part. Okay, so in this particular question, they're asking that in the feedback control system shown in the figure, GS is equal to 6 by S into S plus 1, S plus 2, that is given to you. And this is the block diagram that they have given. They have mentioned that it is a input variable, error variable, output variable. Okay, and they have given a unity feedback system. And what they are asking, if the input RT, okay, if the input R of t is a unit step function, then which is the correct answer, right? That is, they have asked about steady state error. I told you that whenever we apply this final value theorem, okay, that limit t tending to infinity, E of t is equal to limit s tending to 0, S of Es. Okay, Es is the error variable. So S into Es will give you the steady state error. This is ESS, that is steady state error. But we can apply this final value theorem only when, so this is applied by assuming that the system is already stable, that the system is already stable. But here, if you see, this is the open loop transfer function given to you, GS, because HS is 1. So if I apply characteristic equation, okay, so what will be the characteristic equation? So 1 plus GS HS, HS is 1, equal to 0. So 1 plus 6 upon S into S plus 1, S plus 2 equal to 0. So if you see here, this will be S square plus 3S plus 2 plus 6 equal to 0. So the characteristic equation that you are getting is S cube plus 3S square plus 2S plus 6 equal to 0. Now this is a third order characteristic equation. It is a third order characteristic equation. So we can see here that the product of internal coefficient is equal to the product of external coefficient, right? So 3 into 2 is equal to 6 into 1. That is product of internal coefficient is equal to product of external coefficient. So here I can say that system is marginally stable. So the system is not exactly stable, okay, it is marginally stable. And if the system is marginally stable, then we know that the steady state error will not exist, okay, because the error will keep on oscillating. Okay, so I can say here that steady state error, okay, will not exist. Okay, so because if the system is marginally stable, you cannot apply final value theorem. You cannot determine the final value. You cannot determine the steady state value. So how you can apply this error formula? So the error will be indeterminate. The error will be indeterminate. You cannot determine it. And the reason for it is that the error is oscillatory. So option D is the correct answer. Hello students. So this particular question was asked in control system in the GATE 2024 in the GATE 2024 ECE part. So here in this question they're asking that consider a unity negative feedback control system with the forward path gain G of S, and that is given as K by S plus 1, S plus 2, S plus 3 as shown. Okay. What they're asking? The impulse response of the closed loop system decays faster than e to the power minus t if. So here you can see here that they have told that the impulse response of the closed loop system decay faster than e to the power minus t. Okay, this e to the power minus t is the impulse response. So corresponding function will be 1 by s plus 1. So what they are telling is here the reference is not the origin. With respect to this, you have to check the location of the other two pole, and for that they have asked the k value, that is they have asked for the conditional stability. Okay, so पूछा क्या है कि all the poles means here s is equal to minus 1, and compared to this I have to see that all the other pole, that is minus 2 and minus 3, should be lying in the LHS of this. Okay, means decay faster than. Okay, so this will be your LHS now. This part will be your LHS, and this entire part will be your RHS. Okay, and decays faster means what? That means the system is stable. Means this overall system, okay, that is GS, which is mentioned here, the closed loop of this, okay, the closed loop, whatever you will find GS by 1 plus GS, okay, it should be stable. Now they are asking for what value of K or for what range of K this system should be stable. So I can apply Raoult-Hurwitz criteria. Okay, so and I can see about this plane. Okay, because this plane is reference. So S is equal to minus 1 is a plane, right? So I can write S plus 1 equal to 0. So S plus 1, I am considering it as Z. So Z is equal to 0 is your origin. So Z is equal to 0 is the new origin or the reference. Now with respect to this particular line, we have to check whether the poles are lying more negative with respect to this minus 1, means they are lying in the LHS or not. Okay, and they have already told the system is stable. That means all the poles should be lying negative to this minus 1, to the negative of this minus 1. Okay, that means the system should be stable. Now for what value of K? That means I have to apply Raoult-Hurwitz criteria. That means I have to find out the characteristic equation. So characteristic equation would be QS will be equal to 1 plus GS. So let me do this in the next page. So here Q of S will be equal to 1 plus GSHS. I'm finding out the characteristic equation. So 1 plus, what is the function? K by S plus 1, S plus 2, S plus 3. So K by S plus 1, S plus 2, S plus 3 should be equal to 0. So here I'll get S cube plus, this would be 5s square plus s square is 6s square, then 6s plus 5s is 11s, and 3 to the 6, 6 plus k. This is the characteristic equation. Okay, but this is in terms of s, that is here s equal to 0 is the origin. Okay, but I have to check with respect to what? With respect to z is equal to 0. So about z is equal to 0, origin, what should be your characteristic equation? Now here I know that s plus 1, I have considered it as z, as you can see here, right? So s should be replaced with z minus 1. So now I'll get my new characteristic equation in terms of z. So now I'll write q of z. So s cube will be written as z minus 1 whole cube plus 6 z minus 1 whole square plus 11 z minus 1 plus 6 plus k equal to 0. Correct? क्योंकि देखो, for this system, for the closed loop system to decay faster, okay, the real part should be more negative. The real part of this closed loop system should be lying more negative with respect to s equal to minus 1 or z is equal to 0, right? That is why we are applying this. This was the question of relative stability, and we have discussed so many times in the class. So this will be z cube minus 1 a cube minus b cube minus 3 a square b plus 3 ab square. So 3z plus a minus b whole square is a square plus b square minus 2ab. So 6z square, then plus 6, then minus 2z, 6 into 2z is minus 12z plus 11z minus 11 plus 6 plus k equal to 0. So this is z cube. Then 3z square minus 3z square plus 6z square is plus 3z square. Then 3z minus 12z is minus 9z. Minus 9z plus 11z is plus 2z. Then minus 1 plus 6, that is plus 5. Plus 5 plus 6 is 11. 11 minus 11 is 0. So I am left with just k. So this is your new characteristic equation about z is equal to 0 or s equal to minus 1. Now I can apply the condition of stability. Okay. So here if you see, you can do directly also. Okay. For the system should be, for the system, because this is a third order characteristic equation. So product of internal coefficient must be greater than the product of external coefficient. So for the system to be stable, I know that product of internal coefficient. What is the internal coefficient? 3 into 2. So 3 into 2 must be greater than product of external coefficient. What is external coefficient? 1 into k. Okay. So 1 into k. So k should be less than 6. Okay. Also, this value of k should be greater than 0, because I know that from the necessary condition of stability that all the coefficients should be positive. 1, 3, 2 are already positive, so this k should be positive. Okay. Then only this all the coefficient would be of same sign, and that is the necessary condition of stability. So k should be greater than 0. So if you mix this, what I am getting? K should be greater than 0 but less than 6. So this is the range I am getting. So k should be greater than 0 but less than 6. But no option has been given. So one of the option must be lying in this particular range. So 7 to 21, no, not lying. So here, this is not lying here. This is also not lying here. Minus 4 से minus 1, no, not lying. But this particular option, that is 1, because if k is greater than 0 but less than 6, so k can be equal to 1. k can be equal to 2, k can be equal to 3, k can be equal to 4, k can be equal to 5. So 1 less than equal to k less than equal to 5. So this is the correct option. So A is the best fit option here. Okay. So by using this particular range of k, the closed loop system, okay, the closed loop system would be stable with respect to this s equal to -1 plane or z equal to 0 plane. Then only all the closed loop poles will be lying far away from the, okay, this -1 axis, or it will be lying, the real part of that closed loop system would be more negative with respect to s equal to -1 plane. Okay. Hello students. So this particular question was asked from the control system in GATE 2024 ECE section. Okay. So here they are asking that a satellite altitude control system as shown below has a plant with transfer function gs equal to 1 by s square. Okay. So this is a controller. Okay. And it's this one is a controller and it is a double integrator. It is a double integrator. And it is cascaded with a compensator Cs whose transfer function is given to you, where k and alpha are positive real constants. Okay. What they're asking here, in order for this closed loop system to have poles, this one, the value of alpha must be, okay. So here what they're asking is that the closed loop system poles should be like this. Okay. So this should be s, this is -1 plus minus j root 3. So s plus 1 minus j root 3 and s plus 1 plus j root 3. So that will come out to be s plus 1 whole square plus 3, right? So this will come out to be s square plus 2s plus 1 plus 3 is 4, right? So here, if you just take the characteristic equation, okay, because with respect to this pole, I am getting a second order function, right? And what is the characteristic equation from the overall system that I'll get? So characteristic equation would be 1 plus c of s, g of s will be equal to 0. So 1 plus k into s plus alpha divided by s plus 4 will be equal to 0. So from here I'll get s cube plus, no, g of s is s square, right? C of s I have written whatever it was, and g of s is 1 upon s square. Okay. So here I'll get s cube plus 4s square plus ks plus k alpha equal to 0. Consider this as equation 1. So the characteristic equation that I'm getting is third order. Okay. This is your equation 1. And if you see here, then I can have my third order characteristic equation is s plus a, and this is a second order function. Okay. So second order system is your s square plus 2s plus 4. Okay. Because they have already mentioned that in order for the closed loop system to have this particular pole, okay, to have the pole at, so my original system characteristic equation was third order. So I have to make a third order characteristic equation, then only I can compare to have this pole. Okay, for this closed loop system to have this pole, I should have a third order characteristic equation where the second order term is already known, right, from the pole location. So if I just open it, I'll get s cube plus 2s square plus 4s plus as square plus 2as plus 4a, right? I can further take this as s cube plus s square is common, so 2 plus a s square plus 4 plus 2a is common. So 4 plus 2a into s plus 4a. So this is your equation number 2. So this will become your equation number 2. Now compare equation 1 and 2. If you compare, you can see that both are now third order characteristic equation. Now for this closed loop system, to have this particular pole, I should have third order characteristic equation both matching, right? So their coefficient should match. So the 4 should be equal to 2 plus a, k should be equal to 4 plus 2a, and k alpha should be equal to 4a. So 4 is equal to 2 plus a. So after comparing equation 1 and 2, what I am getting? 4 is equal to 2 plus a. Then what I am getting? K is equal to 4 plus 2a. And the last one is k alpha is equal to 4a. So from here, first I'll get the value of a. A is 4 minus 2, that is 2. If I put it here, so I'll get the value of k. So 4 plus 2 into 2 is 4. So k will be equal to 8. And if I put it here, the value of k, so 8 alpha, and a is 2. So 4 into 2 is 8. So alpha will become 1. And that is what they have asked. This value of alpha only they have asked. Yes. They have not asked the value of k, they have asked the value of alpha. So alpha is 1 here. So option B is the correct answer. I hope it is clear to all of you. Hello students. So this particular question was asked from the control system state space analysis part, and it was asked in GATE 2024 ECE. In this particular question, they are asking that consider a system S represented in state space as dx by dt 0 minus 2 1 minus 3 x. So this is the state equation they have given, ax plus bu. Okay, and this is y is equal to cx, that is the output equation. You already know that the state equation is x dot equal to ax plus bu, and the output equation is y equal to cx plus du, right? Where a is the system matrix, b is the input matrix, c is the output matrix, and d is the transmission matrix, right? Now here, if I compare this, so this will be a, this will be b, this will be c, and d is 0. So a I can write down system matrix 0 minus 2 1 minus 3, and b is 1 0, c is 2 minus 5, and d is 0. Okay, so here they're asking that which of the state space representation given below have the same transfer function as that of S. So first find out the transfer function of S. So transfer function of S, how you will write? C into Si minus A inverse B plus D, and D is 0. Now you can see here that this is not in the controllable form, so you have to go by the actual method. Okay, so if I go by actual method, so first I have to find Si minus A inverse. So that is adjoint of Si minus A by determinant of Si minus A, right? First of all, what is Si minus A? This is S00S minus of A. So A is 0 minus 2 1 minus 3. 0 minus 2 1 minus 3. So you will get it here as, okay, s, this will be 0 minus or minus 2 is plus 2, then 0 minus 1 is minus 1, then s minus s plus 3. This is what you are getting. So what is the adjoint of Si minus A? Cofactor transpose. So find out the cofactor and then transpose. So cofactor of S is S plus 3. Cofactor of 2 is minus of minus 1, that is plus 1. Cofactor of minus 1 is minus of 2. And cofactor of S plus 3 is S. So transpose, if you take cofactor transpose, you will get S plus 3 minus 2, 1, S. And what is the determinant of Si minus A? So that will be S into S plus 3 minus of minus 2, that is plus 2. So S square plus 3S plus 2. Right? So this particular part, what you are getting? So C into this Si minus A inverse into B. So C was 2 minus 5. Okay. Si minus A inverse is adjoint of Si minus A, that is S plus 3. Okay. Then minus 2, then 1, then S. And you can divide this entire thing with S square plus 3S plus 2. Okay, determinant. So inverse I have written adjoint of Si minus A divided by determinant of Si minus A into B is 1 comma 1 0 1 0, yes, 1 0. So finally what you will get, this particular part will be, this is 2 by 1, this is 2 into 2, so 2 by 1 matrix you will get. So S plus 3 into 1, so this is 2 minus 5, 2 minus 5, and keep it, this one keep it as it is, that is S square plus 3S plus 2, and this particular part will become S plus 3, and minus 2 into 0 is 0. Okay, this into this, so minus 2 into 0 is 0, S plus 3 into 1 is S plus 3, and this into this, 1 into 1, so this part is 1. Okay, now further, if you just see here, I can see that if you just multiply this two matrix, this is 2 by 1, this is 1 by 2. So I'll get 2 into S plus 3 minus 5. So C by R, that is transfer function. This was my transfer function of S. So C by R, which is nothing but transfer function of S, will be equal to 1 by S square plus 3S plus 2. S square plus 3S plus 2, and this particular part will be 2 into S plus 3 minus 5. 2 into S plus 3 minus 5. So finally you will get 2S plus 6 minus 5, that is 2S plus 1 divided by S square plus 3S plus 2. So this is the transfer function that you are getting, 2S plus 1, S square plus 3S plus 2. So the transfer function here that you got is 2S plus 1, S square plus 3S plus 2. Now you have to check which of which of this particular representation, okay, will give you the same transfer function. Now one by one you cannot calculate the transfer function individually, okay, but I know that these two are in controllable form. This is controllable and this particular part is controllable. So let us check. If the system is controllable, then this system matrix coefficients will be the coefficient of the denominator polynomial of the transfer function, or the coefficient of characteristic polynomial of the transfer function, and this C part will be the coefficient of the numerator polynomial. But we have to write this without sign change and this with sign change. Okay. So if I just find out the transfer function now. Okay. So see here. So for this particular system, you can see that if I try to find C by R, that is transfer function, then I am having numerator polynomial by denominator polynomial or the characteristic polynomial. Okay. Numerator polynomial will be given by C. Okay. You have to go by in this fashion and without sign change. So 2 of S plus 1, okay, divided by denominator polynomial. You have to go in this fashion, opposite fashion, but with sign change. So this is a second order 2 by 2 matrix. So I'll start with S square because order should be 2. Okay. The order of the system matrix is the order of the characteristic polynomial. So S square plus 3 of S plus 2. I have changed the sign. Now if you see, these two are matching. So option A will be your correct answer. Now if you check for the option B also, because that is also controllable, C by R would be, what will be the denominator? S square plus 3S plus 2. But here the output is 2 of S only. So these two are not matching. So this will not be the correct answer. Okay. And this C and D are not, you should not evaluate because option A is giving you the correct answer. So whenever the system is in controllable form, you can directly check. Okay. Thank you all.